all are fine, and I am properly audible there. And also, I hope that the presentation of my screen is visible there. Am I audible there? Okay, fine. And also the presentation is visible there, right? Well, so today we shall be beginning with our next unit. And before I start discussing the contents in detail, let me quickly present a very quick overview of what all is covered in the second unit. So as the title indicates, this unit actually is related to understanding of crystal binding, and then how elastic constants are useful for describing the characteristics of the crystals. Also, role of atomic vibrations in the crystal. So in our first unit, we talked about crystalline materials in very detail. And there, we also assumed that with the help of X-ray diffraction experiments, we can obtain the crystal structure of a substance. And then we also saw one very basic idea that in crystalline materials, the atoms are fixed at specific positions as per the crystal structure, and they are fixed at particular position. So this approximation, this is not exactly true. Means even if we are talking of crystalline material where atoms are supposed to have well-defined positions, even there, actually practically it is nothing like, okay, atoms are perfectly fixed at a particular position. In fact, practically they are exhibiting certain vibrations around their mean position, and those vibrations are important in many aspects because they help in understanding many properties of the crystals. So in case we ignore those atomic vibrations, we term that model as static lattice approximation also, where we are assuming crystal to be something like a rigid body where atoms doesn't move relative to each other. They are fixed at their specific positions. And this approximation is also, I mean, okay to some extent. Many properties works well within this approximation. So we'll be talking about this in the next unit in details. But there are certain properties which cannot be explained within that static lattice approximation. And that is where we actually have to bother about atomic vibrations. So in this unit, we will be talking about atomic vibrations. That, okay, what are the properties which are related to atomic vibrations? So mainly it is actually thermal properties which we will be talking in this unit. Although atomic vibrations have a lot of other important roles also, like they act as a mechanism of resistance for flow of electric current. They have some role in thermal resistivity as well, and so on. So we will be talking something about thermal resistivity, not in very detail, but in brief. But okay, I mean, you should be clear before we move to this topics that why is this topic important, and what is static lattice approximation, and then how we abandon that static lattice approximation and then incorporate motion of atoms, or we should rather say vibration of atoms about their mean position. So this unit actually will begin with this very important and very simple model called Continuum Model. So basically, in Continuum Model, we will be assuming a crystal to be made up of a uniform distribution, or not even if even if it is not uniform, at least we should say the continuous distribution of mass. We don't talk of constituent atoms in detail. We don't talk of interatomic distance as such directly. We treat the crystal as a bulk specimen. We don't bother about its constituents in detail. That okay, what is the crystal made up of? What is the bond strength and all? So that continuum model. So we'll be discussing this in detail. So let me not talk about this in detail here as such. It is following soon in the coming slides. And then we will be understanding how we can understand propagation of elastic waves, means mechanical waves, mechanical vibrations through crystal within this continuum model. Then we shall be talking about now up to this is just crystal taken as a bulk substance. Beyond this, we start talking something about interatomic forces. So we actually are going to the finer detail, means we now are talking of constituents of the crystals. So this topic covers that. I mean, how do those constituents interact with each other, bond formation, bond distance, strength of a bond, etc., etc. Different kinds of potential we will be talking about in this unit. Then we shall also be talking about various other bondings like ionic bonding, Lirard zone type of bonding, covalent bonding and all. So all that is the part of this unit, which will be followed in the coming lectures, not today. Then that's where is this static lattice approximation. I told you what is static lattice approximation. Failures, main failures were related to specific heat or heat capacity of the solid. So okay, when we will begin with the heat capacity topic, I will be talking somewhat in more detail about static lattice approximation. Then we shall be actually talking about those atomic vibrations. I mean, a main objective of studying those atomic vibrations in this unit will be related to the study of thermal properties of the solids, how atomic vibrations leads to specific heat. In thermal as well, we will only be talking about specific heat or heat capacity of the solids. Then we will apply that model to one-dimensional crystal with monatomic basis, then with the diatomic basis. We'll talk all these interesting terms like phonon branches, acoustical and optical phonon branches. And then next will be phonon momentum. I mean, how does phonon behave in a crystal? How does phonon propagate from one point to another point? So what is a phonon indeed? All that will be discussed in the towards this end of this unit. Then we will be applying those concepts which we develop here to understand atomic vibrations. Then those concepts will be applied to actually studying the thermal properties, or rather the specific heat. So we'll be discussing two, or rather three popular models. One was by this one, Dulong and Petit limit. Maybe some of you would have heard of it. Then what was the failures of that model? Then we will be talking about Einstein model and Debye model for phonon heat capacity. And then towards the end, we will be talking somewhat in brief about thermal properties, other thermal properties like, okay, thermal conductivity and thermal expansion of a particular crystalline material. So that's a quick overview of this unit. I hope I could make you clear of the conceptual intention of this unit and what physics we will be talking via this unit. So let us now begin with the first idea of that continuum model. And here we will be actually talking about elastic strains in bulk material. Now, when you're talking of bulk material, you should be actually in a well position to understand what is a bulk material. So we usually call some material as a bulk material. Don't go by the volume or quantity of the material. But okay, literal or conceptual meaning in this context here, or in, I would say, condensed matter physics point of view, bulk refers to the material which is mm, actually considered as large size or large scale material, and there uh, again the bulk material itself, when it is treated within continuum model, then what we do is we assume that bulk material as homogeneous continuous medium rather than periodic arrangement of atoms. I mean, even if we know that, okay, we are studying some crystal, but we don't bother there about how microscopically the atoms are arranged in the crystal. So that's within, I mean, continuum model. Bulk material doesn't exactly mean the continuum model itself, but yes, bulk material is a little different from this. So in continuum model, what we are assuming is we are assuming the material to be made up of a homogeneous distribution of mass. I mean, rather continuous distribution of mass. Homogeneous we can call if the distribution of atoms is uh, uh, homogeneous, and but practically in real materials it may not be homogeneous. At some points we may have some defects, then we may have different mass density there, and so on. I mean, but okay, for the present purpose we shall be assuming this to be homogeneous. So what do we mean by bulk? Bulk means a crystal which is very large in size in comparison to the interatomic separation. That is what we mean by bulk. So then you may ask question that, okay, what are non-bulk cases possible? So if we have a crystal which is large enough so that if you try to see it in all three directions or all three dimensions in such a way that whether it is along x direction or y direction or z direction, the size of the crystal is very large in comparison to interatomic spacing along that direction. So then we will call the crystal can be treated as a bulk crystal. And by bulk, we also mean that, okay, the surface area of the crystal is very, very small in comparison to the volume of the crystal. I mean, ratio of the atoms on surface of the crystal to the atoms in the bulk of the crystal or volume of the crystal is very, very less. Means number of atoms on the surfaces are very, very less. In that case, we call those materials as bulk materials. That's another way of looking at bulk materials. And then you may say, okay, what are the other possibilities? Other possibilities can be like, okay, suppose in one particular direction you cut the crystal very thin enough that the thickness of the crystal is comparable to interatomic spacing, or I mean, it's not exactly equal to the bond length, but it is comparable. Means we can call, okay, the thickness of the crystal is something like, suppose say few bond distance thick, or what we can say, the crystal is few bond distance thick or few unit cell thick, you can say that way. In that case, we will call those materials as nanomaterials. That's a very fancy name for them. Means, or we can say there is a quantum confinement along that direction, because the size of the crystal is very, very less, brought down to the order of interatomic spacing, order of interatomic spacing. So if it is a interatomic spacing, typically is of the order of few angstroms. So if the size of the crystal along that particular direction is a few angstroms or few hundred angstroms even, then we can say that is of the order of interatomic spacing. And those crystals are non-bulk crystals, or we can call them nanocrystals as well. So maybe, I mean, some of you would have studied something related to nanomaterials. Many of our students have done a course on nanomaterials during their BSc. So when you happen to study about that, there you will see that, okay, what is the difference between bulk and non-bulk samples? Anyhow, let's move further and talk about this homogeneous model. Sorry, homogeneous, not homogeneous, but I mean continuum model. So basically, continuum approximation is what I told you. I mean, we assume crystal to be made up of continuous distribution of mass, and rather, in most cases, if crystal is defect free, we will assume that to be a homogeneous distribution of mass as well. And this continuum approximation is, it's not, I mean, it's good approximation, under certain circumstances, but not everywhere. So this is valid for elastic waves whose wavelengths are longer than 10 raised to the power minus 6 centimeter, which refers to frequencies of the order of 10 raised to the power 12 hertz. So now, I mean, you may ask how these two are related. They are, of course, frequency into wavelength. Now, that should be equal to some velocity. So what velocity typically we should take? We may refer here to the velocity, not velocity of light, of course, because in crystal, things doesn't move at the velocity of light, but you can try to relate it to velocity of sound, something like that. So rough orders of magnitude will follow from here, because atomic vibrations can be seen to be some kind of sounds of certain frequencies. So that is how we can relate that to this, and then you can get an idea. Now the question is, wavelength should be longer than this. Why so? Because when wavelengths start decreasing beyond this value, I mean, suppose it is 10 raised to the power minus 9, which is nothing but nanometer, isn't it? So when the wavelengths are of that order, or 10 raised to minus 8, those are of the order of interatomic spacing. So there, the atomic vibrations are such that you have to actually bother about how the atoms are bonded to each other. And then actually you are perturbing the atoms in the crystal at the atomic scales, or even the bond distances are significantly affected. Uh, However, whenever we are discussing the situations where wavelengths are very long, or very long means 10 to minus 6 is the safer limit. So if the wavelength is longer than this, we can assume the crystal to be made up of a continuum of some material mass, so that we can safely go with the continuum model. So below this, we have to bother about those bond distances, and that is where those atomic vibration based models are to be applied. I hope it is clear what is the significance or physical significance of the continuum model. Is there any question from this point? I mean, is this clear what is continuum model and its validity? Or if anyone have any question, please feel free to ask. Yes, any question? Okay, no question. Then meanwhile, I mean, you can also sign your attendance. Just type in your roll number. Well, then basic physical idea is that quantum mechanics is not required in such circumstances. So there is a very good advantage. I mean, there is a benefit why we prefer to go to the continuum model, and we don't need to go to the complex, detailed mechanisms of the bonding, and because that requires at some points, of course, the understanding of quantum mechanics, and we have to apply more complex analysis to such situations. So therefore, in certain cases, when we have to deal with the low frequencies or high wavelengths, then we can stick to this continuum model. And then we can follow the Newtonian's equations of motion. And simple classical Hooke's law can be applied to study of such situations. So under, I mean, again, there is a limitation to this, that Hooke's law is also okay when the strains are not very much large, when the atoms are not stretched very much, or the crystal is not stretched very much, or you don't apply very high stress or strain to the crystal. So there, Hooke's law is okay. But then there may be situations when we go beyond what you call the linear regime. I mean, we are there beyond Hooke's law. I hope you have. Okay. Let us first talk of spring. Then I will be talking what is the meaning of non-linear regime. So I'm sure you all have studied it at your lower classes. What is Hooke's law? It's very simple. That if you have a spring, let's first talk in context of spring. Then if you have a spring, you try to apply some force on a spring. What will happen? That spring will have a tendency to come back to its original position, and when it is deformed from its original or equilibrium position, then what will happen? There will be a restoring force acting on the spring, which will try to bring it back to its equilibrium position. And but this dependence is only there, as long as we don't overstretch the spring from its equilibrium position. If the deformation is within certain limit, which we call the linear regime, or we can call them elastic limit, I think, yeah, then I mean, within those limits, Hooke's law is valid. But when we go beyond that, what may happen? You may get a lesser restoring force. Ideally, what should happen? If you keep on increasing the length of the spring or deformation of the spring from equilibrium position, then force should keep on increasing linearly, isn't it? But then what happens? Because there is a physical constraint, there are physical limitations of the material of which spring is made up, that when you go beyond certain limit, then force is no longer this kind of linear one, and spring is unable to provide large force, actually large restoring force as required by Hooke's law. So that regime, when we go beyond that safe or linear dependence, is called the non-linear regime, linear dependence of force. So when we are beyond Hooke's law, we have to talk about non-linear physics. But here we won't be talking about non-linear physics as such. We will be limiting ourselves to discussion of linear regime. But yes, in future, maybe when you will be required to do some advanced analysis, there you practically may have to incorporate non-linear terms. So when you are talking of non-linear terms, this whole analysis of linear physics should be there in your mind, so that you know that, okay, what you are going to do in non-linear case. Well, then in general, so that's the Hooke's law for one-dimensional case. I mean, you are talking spring to be one-dimensional. There is only one direction along which deformation is possible. But practically, in material, when we are talking of a crystal, that is a three-dimensional object. So that linear case is a very simple and trivial case. In case of real materials, we have to generalize this, and this can be seen as sort of a general form of Hooke's law. Or Hooke's law, we can also call Hooke's law, actually is nothing but it relates stress to strain. What is stress? Is force per unit area, right? In case of 3D material, we will be actually preferring to work in terms of stress and strain. And what is strain? Is deformation produced per unit length, correct? So Hooke's law is nothing like stress is proportional to strain, or if, and this is what we call the spring constant. So similar kind of form exists for Hooke's law in 3 dimensions. So basically, I mean, for a 3-dimensional material. So in general, Hooke's law is the law which relates stress with strain. So here, that is how we can write down that sigma is equal to Fij, which is function of E11, E12, E13, and so on. Now I will be talking about this. So what is this sigma? Sigmas are representing stress components. So I mean, stress means related to force, right? Okay, this is not force actually. Okay, fine. I'm sorry for that. So this is stress. It is a function of strains. Means same thing like here. I mean, stress. If I take this divided by area, this will become stress. It is some function of strains. This is say deformation per unit length. And what is the functional dependence? It is linear dependence. So in general, for a 3-dimensional case, we can say that stress developed in a crystal actually is some function of the strains existing there, or you can call it otherwise also. I mean, if you apply some external stress, then that is a function of the strains, or accordingly the strains will be produced, which will depend upon what is the stress. So what are these Ij? I and J actually are related to the dimensions of the crystal. So 3-dimensional crystal, you will have 1, 2, 3. They are up to 1 to 3 only. I mean, you will have, say, you can assign 1 for X direction, 2 for Y direction, 3 for Z direction, and that's all. So accordingly, what will be the strains? I mean, say epsilon 1 means xx, xy, xz, then epsilon yx, yy, yz, and so on. We will be discussing the physical relation. I mean, physical interpretation of these stress and strain things for a three-dimensional case. They are following up in the next slide. But okay, I mean, one thing which is important to note here is that this dependence within Hooke's law is linear, but practically, I mean, in many situations, this may be non-linear as well. Well, I mean, now, if we actually expand this function in terms of Taylor series, then what, and if we retain up to first order term, and that's what actually refers to the Hooke's law, and that's what we call the linear, and that is the material which we call the linear elastic material. If we retain, so in general, I mean, if you have some function, then that function within Taylor series, I hope you know, that is equal to, say, function defined at certain points, say y naught, plus we can say del y over del x into delta x, plus del square y over del x square into delta x square, and so on, isn't it? That's what is the Taylor series. So if we ignore the higher order terms and only retain terms up to first order, then that is what comes under Hooke's law, and we call that as linear regime. Fine. So in that case, what we will be having 9 stress components. Why 9? Because we are taking I is equal to 1 to 3. I mean, x, y, z, you can say. Then there will be, say, sigma 1 1, sigma 1 2, sigma 1 3. Then sigma 2 1, sigma 2 2, sigma 2 3, sigma 3 1, sigma 3 2, sigma 3 3. So total 9 stress component for a three-dimensional material. And then we will be having 9 strain components as well. And these are what we call the elastic constants of a material. We'll be talking about these in detail. So we will be having total 81 elastic components. Why 81? You can see the combinations here. And this same equation actually can be written, okay, I mean, this equation can be written in terms of this matrix form. So this matrix form is the generalized form of Hooke's law, and this matrix form will relate stress with the strain. So if I have to find out sigma 1 1 means stress along say x direction, we will be seeing the meanings of sigma 1 1 and sigma 2 2 and so on. So how we can find out with the help of this matrix? Sigma 1 1 will be equal to C1 1 1 into epsilon 1 1 1, C1 1 2 2, epsilon 2 2, C1 1 2 3, and so on. I mean, that's how we can find out various stress components, given provided you have been given the strain components to you. Or you can do other way. Suppose somebody gives you, this is the strain I apply on the crystal, find out the stress. So you have to apply inverse of this matrix. So this is the general form of Hooke's law for any anisotropic material. So what is the physical significance of these sigma 1 1, sigma 1 2, and so on? Can be understood from this figure. So we can assume our material, because we are talking of continuum model, so we don't say, okay, this is this crystallographic direction, this is that crystallographic direction. No, we simply try to take, suppose, a crystal of some, say, cubic shape. I mean, external shape of the crystal, suppose, is cubic. Internally, it may be BCC type of crystal, or tetragonal type of crystal, hexagonal type of crystal, but we can cut it externally in a cubic shape, isn't it? Over the bulk length scales. So in that sense, we are saying, okay, suppose this is one direction. I mean, we can say X direction, this is a Y direction, this is a Z direction, 1 2 3 refers to that. Then what is sigma 1 1 is actually the stress along first direction. First one tells the direction along which the stress is applied, and second one tells that okay, on which phase it is acting. Okay, this will be clear shortly. So sigma 1 means one is the direction along which it is acting, and second one is referring the face perpendicular to this direction, one direction. So what is the face perpendicular to one direction is this face. So sigma 1 means stress acting along one direction on a face perpendicular to this axis. And what is sigma 1 Now let us see this one, correct? Sigma 1 Now sigma 1, first one tells you the face on which it is acting, and second one tells the direction. Sigma 1 means this one. This is sigma 1 Note it carefully. Okay, vertically upwards. Sigma 1 means the stress acting on face perpendicular to 1. I mean this face. And what is 2 means sigma, a stress directed along 2 or y-axis, let us say. So this is your sigma 1, 2. So this is a physical meaning. I mean, because stress can be applied on this face this way. It may also be applied along this way. You may call shear stress, correct? Similarly, you may have sigma 1, 3. Okay. And in the same way, we can call something like sigma 2, 2, sigma 2, 1, sigma 2, 3, and similarly sigma 3, 3, 3, 1, 3, 2, 3, 3. Is it clear how to understand the physical meaning of these stresses or these stress components? Is this clear? Okay. And this analysis is not only applicable for study of elastic strains, but it can also be applied, or this kind of notation is also applied in case of electrical properties of the crystal. For example, when you apply Ohm's law, there we have conductivity is proportional to what? Or you can call other way. I mean, current density is proportional to electric field, isn't it? Sigma is proportional to E. Current density is proportional to electric field. And then accordingly, you have a constant of proportionality there. So there also, I mean, conductivity can be along X direction, Y direction, Z direction, and then you will have you can also have electric field along X direction, Y direction, Z direction, and then you have a conductivity tensor, right? So I mean, I hope I'm not saying it wrong way. Oh, we have to call that current density, not conductivity. If I told it wrong way, sorry for that. I mean, current density is proportional to electric field, and current density is equal to sigma into E, isn't it? I mean, that's how we write it, I think, where the sigma we can call as the conductivity tensor. So you may have current density is equal to sigma 1, electric field 1. Similarly, current density along say 1. Similarly, current density along 2, say, or y-axis will be like, okay, sigma 2 into EY. I mean, it depends upon what kind of crystal it is. If it is anisotropic crystal, then your conductivity is going to be a tensor quantity, which will be having 9 components. Something like you have 9 components here, okay? Sigma 1, sigma 1, 2, and so on. So this analysis, I mean, mathematically will be looking like similar in both contexts. So that is why physical meaning should be clear. So what is the meaning of this is, now let us try to relate this now, this equation, and then try to understand what is the meaning of various terms appearing here. And now, okay, you will say, okay, why only these faces are shown? Why not opposite faces? So opposite faces, we don't need to talk as such in terms of independent components. Sigma 1 itself is representing a direction. Then other face actually is represented in terms of the same. And then we talk of, say, X dependence of sigma. So we may call sigma 1 is depending upon X. If it is not uniform, then stress may be different. I mean, stress here may be different on this phase. Stress somewhere in middle of this cube may be different, which is acting along, say, X direction. Stress here may be different. So that is where we actually define that in terms of X dependence of sigma. So only these 9 components of stress and 9 components of strain are important. So are they 9? Yes, we have 3 faces and 3 components on each face. So that is what is representing those 9 components. And this is the Hooke's law, relating these 9 stress components with 9 strain components. Just similar to the stress components, we will be having strain components as well. Epsilon 1, epsilon 1, 2, epsilon 1, 3, and so on. Yes, somebody is trying to say something or ask question. Yes, please. Is there any question? Is there any question? No. Okay, fine. Okay, let us try to understand physical meaning of this. So basically, if we try to see this, say, let us take the product and bother about first column only, first element. What will be sigma 1, 1? So sigma 1, 1 is equal to C 1, 1, 1, 1 into epsilon 1, 1, then plus C 1, 1, 2, 2, epsilon 2, 2, and so on. So what is this telling? That stress along x direction, or I mean stress on this face acting along this direction perpendicular to the face is not only depending upon strain along this. If it would be linear case, then sigma 1, 1 equation would have been very simple, Hooke's law. Sigma 1, 1 should have been equal to something like C 1, 1, 1, 1 into epsilon 1, 1. Correct? Means that's what is the Hooke's law. This one means stress along x direction is proportional to only strain along x direction. That's it. Correct? But here the situation is more generalized. Means stress along x direction is not only depending upon strain along x direction, but also on strain along y direction. There is corresponding constant of proportionality for that. Similarly, strain along z direction as well. This is you would say um, longitudinal strain, I think. Then there may be shear strain along other directions as well. So means the stress along one direction depends upon overall strain in the body along various directions. That's what is important. So I mean now actually it depends upon, so there may be case that okay, there is no strain along one direction. Let us assume 1 is 0, epsilon 1 is 0. Still you have a stress along one direction. So what is it coming from? It may be coming from strain along say 2 direction, or from 3 direction, or from other. I mean that is how we can try to understand stress strain relation. I mean this depends upon what is the values of these constants. So usually these diagonal elements are representing the longitudinal strain, right? I mean the strain or stress produced along one direction because of strain along one direction. So usually in many cases or most of the materials, these components are largest, and it is okay also. I mean within common sense that is fine. Means when you are applying strain along one direction, means you have a crystal trying to stretch it along one direction, then there will be maximum stress along one direction. Means there will be maximum restoring force along one direction, isn't it? That's a straightforward one-dimensional analysis. But then it may happen that okay, you are applying say stress along say y direction, and crystal gets elongated along x direction to balance the stress, isn't it? So that is how various possibilities are there, and that's what these components do characterize. So if only diagonal elements are non-zero, off diagonal elements suppose are all zero, then the material is very simple isotropic material, and is following Hooke's law, and Hooke's law, and of course there is no of diagonal dependence. I mean, the stress along one direction is not depending upon strain along two direction. Means even if you apply strain along two direction, means y direction, let us assume, then there won't be any stress along x direction. So that kind of situation. But practically this doesn't happen. So all these, I mean, at least few of the elements close to diagonal elements are non-zero. These are largest usually diagonal elements, then these are smaller in comparison to them but non-zero, and then all others which are far away from the diagonal location are close to zero. So that is how we can understand these three-dimensional form of Hooke's law and how we can relate these various stress and strain components to each other. Rahul Singh is asking something. Okay, we often talk about strain of the bulk material and even in thin film. So what information it gives us? So we are going to that in, I mean, coming slides. We will be discussing all these analysis in detail. Then there I will be talking a little much detail about this. So let us try to talk of those strains. So I talked to you about those strains. I mean, there is a possibility of longitudinal strains. I in detail talked about this. And there may be shear strain. There may be volumetric strain, means overall compression of the body. So let us now try to discuss that generalized formalism and try to understand those stress strains. And then we will be applying this to a simple case of cubic crystals. We will keep our life simple. So here we will be only discussing the what you say, the generalized formula, formalism actually, or a method. Then we will be applying that method in simplest case, not to make our life simple. Then if you have to make it more generalized, then you may have to do a little complex analysis. But okay, we will be discussing those generalized aspects. Now let us define strain components. Now earlier we were calling them epsilons. These are actually deformations, and deformation and strain, they are related to each other. Like okay, the strain is deformation per unit length. That's like strain. So let us, these are suppose how many? 1, 2, 3, 4, 5, 6 components. So what we are saying is only from 9 components we went back to 6. Why so? Because epsilon xy will be same as epsilon yx because of some symmetry requirements, not exactly the symmetry requirements, but because we are ignoring the translational or rotational effects of the body. This is coming up in the next slide, so let me not mess up with that here. In the coming slides I will be clearing that. Okay, for time being what we are saying is okay, sigma, or sorry, E xy is same as Eyx, Eyz is same as Ezx, and Ezx, sorry, Eyz is same as Ezy, and Ezx is same as Exz. So this reduces those number of components, or in terms of this we are saying sigma 23 is same as sigma 32, sigma 12 is same as sigma 21, and sigma 13 same as sigma 31. So the 9 components actually reduces to 6 components. So why so? I will be coming in the next slide. So now to discuss the analysis further, let us assume that okay, we had a cubic crystal or a material. Cubic means, doesn't mean simple cubic, but we had a bulk crystal of cubic shape, suppose, or it can be of any shape. But now what we are saying is okay, we are trying to characterize unstrained crystal with respect to a strained crystal. So if the crystal is unstrained, let us draw 3 mutually perpendicular axes within the crystal, so that the location of whenever these 3 crystals are mutually perpendicular to each other and their length, suppose they are 1 unit, and their lengths are 1 unit, we say crystal is unstrained. Fine. Now, how we are trying to understand strain is that, okay, when we apply strain on the crystal, then these axes, these are fixed, right? So these are fixed within the crystal. Locally, they are fixed. So whenever I strain the crystal, then suppose this axis in contact with certain specific atoms somewhere here, then it is in contact with some other atoms specifically here. So whenever we strain the crystal, the atoms will be changing their position relative to each other. So will happen to these mutually perpendicular axes. Means the deformation actually of the crystal can be characterized in terms of change in angle between these axes and also the change in length of these axes. So that will be defining the strains or stress inside the crystal. Is this idea clear? Why we are choosing these axes? Is this clear? So this analysis has been copied from Kittle's book. So I would recommend you to go to Kittle's book for details. Well, so I mean, then how we can relate those new axes in terms of old axes? So suppose these are now new axes of a deformed crystal, then how we can define them mathematically in terms of old axes? We may say, okay, x dash is equal to, say, suppose 1 plus e, this is deformation now, e x x x cap plus e x y y cap plus e x z z cap. Notice one thing here, that we are defining x dash something like, okay, this was originally x, now this is your x dash, so now x dash is related to x, y and z. What does it mean is that change in length and direction of axis because of deformation produced along x direction. So originally it was having length, say, 1 unit. Now we are saying, okay, there is some deformation, so 1 plus exx. Similarly, there may be deformation along y direction, which may lead to change in the x component of the new axis. There may be deformation along y direction, and that may cause change in either length or direction of x axis. There may be deformation along z direction, which may cause change in orientation or length of x axis. So this is representing that. Similarly, other equations. Okay, so this relates, and these are called deformation. So epsilon, alpha, beta are called deformations. That's okay. So is this relationship clear? I mean, how the two are related, or any question from this? Any conceptual confusion which may have arisen, or it is okay? Well, clear. Now, we will be establishing some mathematical relations between them so that we can then further proceed for the analysis of the strains. So one more thing which we should notice here is that these deformations are very, very less. So actually we are talking within continuum model, and that too within linear regime. So we will be in linear regimes only when the deformation is very less in comparison to the length of the spring, that is as per Hooke's law. Or what we can say is that, okay, whenever we are deforming the crystal, the deformations are very small in comparison to interatomic spacing. Means it is like, okay, the bonds are not stretched very much or compressed very much. That's what is the meaning of this. So they are very, very small in comparison to 1. Means epsilon xx, epsilon xy. These are all very small in comparison to 1. The original axes, so, were of a unit length, as we already discussed. But now new axes will be of a different length. They are not necessarily of 1 unit length. So what will be the change in length that we can determine by taking dot product? Because this was a unit vector earlier. X dot x was to be 1 in earlier case, correct? So what will be x dash dot x dash? That now you can take self product here. So what will this be? This will be 1 plus epsilon xx whole square. Right, so that we can write down 1 square plus epsilon xx square plus 2 into epsilon xx. So that is why this term, and then epsilon x square, then this will be giving this, and so on. Correct? Now, if we assume that the strains are very, very small, not very large, or deformation is not very large, then we can neglect these higher order terms. I mean, square. I mean, if epsilon xx is very small, something like 0.01 or 0.001, what will be epsilon xx square? That is going to be very, very small. So, okay, we can say the deformation in x-axis or change in length of x-axis can be retained only up to first order. Similarly, we can write down the other components as well. Now, if we actually take any point within the crystal, okay, so let me go back to the previous slide. So suppose now try to imagine a crystal around this. Maybe in next lectures, I will draw a cube here. And then try to find out one point in the crystal, somewhere here, suppose this is 0, 0, 0, some points here in the crystal, some arbitrary point. So in unstrained crystal, that point would have been located somewhere here. That would have certain, what you can call, that would have certain components, right, or position vector. Now, suppose this is that point in unstrained crystal. Now, because of strain produced, this point will be shifted with respect to its original location, and then that point can be defined in terms of new vectors like this. What we are assuming is that suppose the fractional coordinates of that point in the new coordinate system remains same. Suppose it was originally at 0.5, 0.5, 0.5, means suppose center of the cube. Suppose originally it was at center of the cube. So here as well, it is exactly in the center. It is 0.5, 0.5, 0.5, but deformed. And the deformation is now taken care in terms of x dash, y dash, z dash. I hope that's clear to you. So that the displacement now can be defined using this simple equation. And then we can substitute these values here to obtain the displacement. What we have done is we have substituted these values because x dash, you know what is x dash? So x dash is substituted here, y dash is substituted, z dash. Then finally you arrive at this equation. Now, since we are running out of time, I would stop here, but I would request you to do this yourself properly in your notebook so that you are not confused at how this comes directly. Just substitute the values and get the terms here. So then we will be talking about further analysis, and there was one question how these strains can be related to the experimental measurements. So we'll be talking about them in the next classes, and then there are a lot other things to follow. We'll be discussing that in detail in the next classes. Anyway, so that's all for today. Is there any question from today's class? Then please ask. I will be happy to help you. Yes, any question, please? Am I audible there?
Yes, sir.
Okay, so
Sir.
Okay, yes, Sandeep.
Sir, actually we are considering in continuous model. But we have taken epsilon alpha beta comparable to the interatomic separation. Then why we are taking that?
No, I am not saying epsilon alpha beta is comparable to interatomic spacing. I said, or sorry if I said it like that. I mean, this is not of the order. It is very, very small. It is to be very, very small in comparison to 1. Means it is very, very small, very, very small in comparison to interatomic spacing. That's what it meant. Of course, when we will take epsilon, I mean these epsilons comparable to the interatomic spacing, then of course we have to go to the other situations. Then things are not comfortable that way.
One more question, sir. here we consider lambda less than 10 raised to power minus 6 centimeter.
Uh,
Then bond strength is significantly affected. But if we
why?
consider 10 raised to power minus 9 angstrom or in the order of a nanometer, then what
Hmm.
happens, sir?
Then what you're saying, bond strength is affected? No, I don't think bond strength is affected for 10 to minus 6 centimeter. But yes, when you go to the nanometer regime, bond strengths will be, we can't say bond strength will be affected. It is actually related to that energy versus bond distance curve. I hope you would have seen it somewhere.
Yes, sir.
That anisotropic curve, actually, whenever we try to bring two atoms too close to each other, the repulsion dominates and it is very sharp curve. And then when you try to bring atoms away from each other, then it follows some minima, and then it is an anisotropic curve, and then it goes towards a constant value.
Yes, sir.
I hope you could recreate that curve in your mind.
Yes, sir.
Then, when we are saying that uh, the 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 analysis is linear, or we can say it is of the order of interatomic spacing, not very large. What do we mean? There is actually, we are following harmonic approximation. I mean, near the minima, we can approximate that curve to be like a parabola.
Yes,
Okay.
sir. Yes, sir.
So within that parabolic approximation or harmonic approximation, we can still apply Hooke's law, and we are still within a linear regime. But then we may not be, I mean, talking of continuum model at all. I mean, it's not necessarily the continuum model, because continuum model means we are talking of these epsilon i's or sigma j's, whatever they are. We are talking of them
Yes, sir.
in bulk form. We don't derive them from interatomic characteristics, like from that potential energy curves. So it is very simple. I mean, you take Hooke's law. If you have to, these are like these constants. I think I have quit the PPT, but then I hope you remember those constants which are relating stresses to strains, correct?
Yes,
In
sir.
case of
Yes, sir.
Hooke's law, we can find out it is like K. For one dimensional case, it is like spring constant,
Yes,
correct?
sir.
So
Yes, sir.
how we can get those constants? They can actually be followed from the this potential energy curve. If you take half kx square, then we can fit that to a parabola and then find out the values of k, correct? But that
Yes,
is
sir.
good only within the harmonic approximation, or we can say parabolic approximation. If the curve is anisotropic, we are taking strains which are large, then that won't be the case. And then these components are not that straightforward. I don't know if I could answer your question, or is your question somewhat different from
सर
what I.
यस सर माय क्वेश्चन वाज डिफरेंट बट
Yeah.
ये था सर क्वेश्चन कि जो हमारे पास कंटिन्यूम जो अप्रोक्सीमेशन है वो
Hmm.
हमारा इलास्टिक वेव्स के लिए वैलिड है जिनकी जो वेवलेंथ है 10 रेज़ टू पावर माइनस 6 सेंटीमीटर से ज़्यादा होगी।
हाँ बिल्कुल।
तो सर अगर वेवलेंथ 10 रेज़ टू पावर माइनस 6 सेंटीमीटर से कम जाएगी
जी।
तो उस केस में क्या होगा? बस यही क्वेश्चन होगा।
उस केस में आपको एटॉमिक वाइब्रेशन स्टडी करनी पड़ेगी। आपको इंटरएटॉमिक बॉन्डिंग स्ट्रेंथ्स के बारे में बात करनी पड़ेगी। दैट इज व्हाट इज फॉलोइंग इन द कमिंग टॉपिक्स। वहां पे आप उसके बारे में बात करेंगे। हायर फ्रीक्वेंसीज विल हैव टू बी डेल्ट। तब वहां पे हम उस जो पोटेंशियल एनर्जी वर्सेस एटॉमिक डिस्टेंस कर्व है, कहीं ना कहीं उसकी बात करने लगेंगे।
यस
ठीक है।
ठीक, थैंक यू सर।
No, well, if there